In this brief video, we're going to show you how to solve the standard cost minimization problem that a firm faces. Let's state the problem first of all. This is the cost minimization problem. So the firm wants to minimize its total costs, which are the sum of the amounts it spends on its inputs. If it has two inputs, labor and capital, then the amount spent on labor is the price of labor times the quantity it buys, plus the price of capital times the quantity it buys. So cost is equal to spending on labor plus spending on capital, where PL is the price of labor and PK is the price of capital. And the firm wants to minimize its total cost subject to the constraint that the required output, which we'll call Q star, is governed by the production function. And the production function we've written previously as the function of L and K. So here's the statement of the problem. It's a constrained optimization problem. We want to minimize the cost of production subject to the constraint that output is produced according to the production function using inputs L and K. We know that to solve constrained optimization problems, we can use the Lagrangian theorem. And the way we set up the Lagrangian function is that we take the function that we want to minimize and we define a new function, C star, which we know to be PL times L plus PK times K. And we want to add on a Lagrangian multiplier, which we'll call minus lambda, times the constraint, which is the production function, with the constraint written in such a way that it's equal to 0. And we know from the Lagrangian theorem that doing an unconstrained optimization of this Lagrangian function is equivalent to optimizing or minimizing costs subject to the constraint in the production function. So we know it's pretty straightforward to optimize this function. What we want to do is we want to compute the derivative of C star with respect to L, with respect to K, and with respect to the Lagrangian multiplier lambda. So the first of these terms is PL plus the partial derivative, want lambda here, plus lambda times the partial derivative of F with respect to L. We want to set that equal to 0. And then the second term, the derivative with respect to K, is PK plus lambda times the partial derivative of F with respect to K, and we want to set that equal to 0. And the partial derivative of the Lagrangian function C star with respect to lambda is, of course, just the constraint, Q star minus F of L and K, and that's equal to 0. And we can see what we have here is three functions, 1, 2, 3, and basically three unknowns, the amounts of labor, capital, and cost. And we can manipulate these to find the rule for optimization. What you want to do is solve these first two functions for lambda, so that minus lambda is equal to PL divided by the derivative of f with respect to L. We know that to be the marginal product of labor, and minus lambda from the second function here is also equal to PK divided by the marginal product of capital, because this partial derivative is nothing other than the marginal product of capital. Two things equal to the same thing are equal to each other, so we can write the marginal product of labor divided by its price is equal to the marginal product of capital divided by its price. Or you can, if you wish, this is one way to write the rule for minimizing cost. There's another way you can write it, put the prices, this is a K down here, is to write it this way: PL over PK is equal to the marginal product of labor divided by the marginal product of capital. So you can have it either way you like. Way one down here, the marginal product per dollar spent on labor has to be equal to the marginal product per dollar spent on capital. The other way of writing it says that the ratio of the prices of the inputs, the price of labor divided by the price of capital, has to be equal to the ratio of the marginal product of labor divided by the marginal product of capital. Now, if your memory is pretty good, this ratio of marginal products is really the marginal rate of technical substitution of labor for capital, which we derived when we talked about the production function itself. We know the marginal rate of technical substitution of labor for capital is just the numerical value of the slope of an isoquant. And so we see that cost minimization occurs when the marginal rate of technical substitution of labor for capital is equal to the ratio of the prices of the inputs. That's just another way of saying that the slope of the isoquant, the green line here, has to be equal to the slope of the cost constraint. So what we're looking for is a point of tangency between the isoquant and the cost constraint. If the firm were operating on this lower cost constraint, choosing inputs according to that cost constraint, there's no way it could achieve the desired output, Q star. On the other hand, if it operated along this upper cost constraint, we can see that it can produce a much larger output than Q star. And so it would be wasting money. It would be spending too much in order to produce the output Q star. So again, to repeat the rule, we want the margin rate of technical substitution between the inputs to be equal to the ratio of the prices, or what is equivalently the same thing, we want the marginal product per dollar spent on all the variable inputs to be the same.